Hello, my name is Tom Talatonis, and this is my lab report. In this lab report, I'll first go through an introduction, then review the relevant concepts, talk about the setup of the experiment, then the model that was simulated through GlowScript. I'll answer questions about it, and finish with discussion questions. The purpose of this lab was to use Faraday's law and learn about it through the experiment of a magnet falling through an aluminum tube. Some relevant concepts are Faraday's law / Lenz's law, Ohm's law, magnetic force, induced fields and currents, and the magnetic field of a dipole. Some key results from the experiment was that average time the magnet took to fall through the foil was 1.256 seconds, and the simulation time from the GlowScript model was 1.352 seconds. Now on to the review of the relevant concepts. Faraday's law, also known as Lenz's law, states that the EMF is equal to the negative derivative of flux, which is basically that voltage is equal to the negative derivative of flux. Ohm's law states voltage is equal to current times resistance, and we can apply Ohm's law to Faraday's law to get current from the flux. Magnetic force is the force of charged particles due to their motion, and one formula for it is charge times the velocity cross product of B. Then there's induction. Through a change in magnetic flux, a magnetic field is induced in the opposite direction of change. This leads to an induced current and an electric field. And finally, the magnetic field of a dipole is equal to mu naught of 4 pi times 3 r hat times r hat dot m, which is the magnetic dipole moment, minus m over r cubed. In the experiment, the magnet was dropped through the foil 5 times, and I recorded the time it took each time. The first was 1.24, and as stated is the rest of the trials. And some key things we need to know was that the magnetic dipole moment was 1.15 joules per Tesla. The length of the foil was 0.31 meters. The width of the foil was 0.007 meters. The inner radius of the foil was 0.021 meters, and just using a simple math, the radius of the foil was 0.028 meters. The mass of the magnet was 0.024 kilograms, and the average time it took was 1.256 seconds. On the screen, I have the relevant code. This is the key parts of the code, which shows the parts that I directly edited, from figuring out what the dipole function would be to the derivative of flux over the derivative of time function, and then this was then applied to get the model as well as the velocity versus time graph. In the model, we can see that first it's there's a little loop, but then it becomes constant. This constant velocity, which I will also answer later, is representative of the zero net force of the magnet during the flow. And as you can see, the simulated time was 1.352 seconds. Okay, so the intensity of the coloring on the tube indicates the magnitude of current flowing through each ring. Red and blue indicate current flowing in opposite directions. Which color corresponds to clockwise and which one corresponds to counterclockwise, and how can I know? Red corresponds to counterclockwise and blue corresponds to clockwise. The counterclockwise is the one responsible for attracting the magnet, whereas the blue repels it. So that means the red must be on top, even though the previous slide didn't show it, the red was on top in the model. Second question, what happens to the dynamics of the system when you flip the magnet around? Nothing, just the currents will be flipped. Third question, way to make it more accurate would be to make the dt in the code smaller, so it will just be more accurate because of these smaller portions. And what is the shape of the velocity versus time plot? Like I said earlier, it means that their net force of fall is 0, as it has a constant velocity, which means no acceleration. Answering the first what if discussion question, the current would be increased, resulting in the magnet having slower descent. And then answering the second question, the holes would disrupt the current, making the current flow smaller. This will result in a smaller upward magnetic force, which in turn would mean that the magnet will fall faster.